The rate equation is very important to us in the study of kinetics, and there are some factors that affect the rate of reaction. These include reactant concentration and temperature. In rare cases, product concentration can also affect the reaction rate. A generic rate equation is provided for you. Rate is equal to K times the concentration of A raised to some exponent times the concentration of B raised to some exponent, and that would continue through any other reactants that you may have. Now, K is the rate constant, and this rate constant is constant as long as you're at a steady temperature. If the temperature changes, so will K. So you have to watch and see what the conditions of the reaction are. When we do problems, generally we will always assume that the temperature remains constant so that K does not change during that. When you see the exponent symbols here, M and N, these represent the order of reaction. And the order of reaction is how changes in concentration will affect the reaction rate. And we'll be determining those as we go along here. Determination of rate order, we're really solving for what the exponents, M or N, the symbols from the generic equation are. If that exponent is 0, the reaction order is 0. If the exponent is 1, the reaction order is first order. But when it's first order, we generally don't show a 1 there. You would just show the concentration in brackets. If the exponent is 2, then the reaction order is 2. Here's what it means. If the exponent is 0, zero order reaction, changing the concentration of the reactant does not affect reaction rate. For instance, if we double the reaction rate as shown here by putting the 2 inside the brackets and raise that to a power of 0, it's equal to 1. If the exponent is 1, then doubling the concentration will double the rate. So here we show 2 raised to the first power, which is 2. And if the exponent is 2, doubling the concentration will increase the rate by a factor of 4. And here you see the 2 inside the bracket squared is equal to 4 times the reaction rate. Predictions involving kinetics are impossible if you do not know the rate order. So let's look at how we determine this. Let's consider this reaction. Here we have 2 nitrogen monoxides reacting with oxygen gas will form 2 nitrogen dioxides. And in this table you'll notice that we have 3 different experiments where the concentrations of the reactants of the nitrogen monoxide and the oxygen vary from experiment to experiment, and then the rate at which nitrogen dioxide formed is given as well. And what we're going to do when we want to find what the rate order is for a particular reaction, we want to look at 2 experiments where the concentration changes for that reactant and the concentration of the other reactant does not change. So for instance, as I'm looking at nitrogen monoxide, it changes in concentration from experiment 1 to experiment 2, but the oxygen stays the same at 0.1 moles per liter for both. And then if you look at the rate of nitrogen dioxide formed, you'll see that that rate changes as well. So when we examine nitrogen monoxide, we're going to compare experiments 1 and 2. For oxygen, you can see that its concentration changes from experiment 1 to experiment 3, or from 2 to 3. And we would have to make a determination which pair we would want to use based on what happens with the nitrogen monoxide. Because the nitrogen monoxide is the same in experiments 1 and 3, whereas the oxygen varies between experiments 1 and 3, we would want to compare those 2 experiments. Here's a generic rate order equation. So here we have the concentration of A from an experiment that I have marked prime over the concentration of A from another experiment raised to some power x is equal to the reaction rate for the experiment prime over the rate of the other experiment that we're looking at. X would equal the rate order for A. So we're looking at the ratio of the concentrations raised to some power is equal to the ratio of the rates. And we just need to make sure that we keep our experiments, the data from which experiments consistent. Let's do nitrogen monoxide first. We're going to take the concentration of nitrogen monoxide from experiment 2 over the concentration of nitrogen monoxide from experiment 1. That ratio raised to some power x will equal the reaction rate from experiment 2 over the reaction rate from experiment 1. Again, x is the rate order for nitrogen monoxide. So we have our 0.2 moles per liter divided by 0.1 moles per liter raised to some power x is equal to 2 moles per liter times seconds over 0.5 moles per liter times seconds. So we have that ratio of the concentrations is 2 raised to some power x is equal to the ratio of the rates, which is 4. So 2x, 2 raised to a power x being equal to 4, that means x has to be 2. So the rate order for nitrogen monoxide is 2. From our previous calculation, we've determined that the rate order for nitrogen monoxide is 2. So next we're going to do the oxygen. Now oxygen, we're going to use the concentration from experiment 3 over the concentration from experiment 1 raised to some power x is equal to the ratio of the rate from experiment 3 divided by the rate from experiment 1. And that will give us the rate order for O2. So that concentration ratio would be 0.2 moles per liter divided by 0.1 moles per liter raised to some power x will be equal to the ratio of the rates, which is 1 mole per liter times seconds on top divided by 0.5 moles per liter times second on the bottom. The ratio of the concentrations is 2 raised to some power x is equal to the ratio of the rates, which is 2. So 2 raised to some power x being equal to 2, x here would equal 1. So for oxygen, the rate order is 1. Once we know the rate orders of the individual reactants, for instance here we know that the rate order for nitrogen monoxide is 2, the rate order for oxygen is 1, we can then write the overall rate equation based on this information. So our rate will be equal to K, which is the rate constant, times the concentration of nitrogen monoxide squared, times the concentration of oxygen. Because oxygen is first order, that 1 does not have to be written. When it's left off, it's implied to be 1. So it's just like when you look at the subscripts in a chemical formula. If the subscript is 1, we don't write it, it's just assumed to be there. So now that we have this written, we can also find our overall rate order for the reaction, which is the sum of the exponents. So here it would be 2 for the nitrogen monoxide plus 1 for the oxygen gives us 3. So this rate overall is a third order reaction. We know some things. We know, for instance, the rate of reaction at certain concentrations of nitrogen monoxide and oxygen to form nitrogen dioxide. We also know the rate orders for both nitrogen monoxide and oxygen. That's what we just finished calculating. So what we want to do now is taking a look at the rate equation. There's one thing we don't know, and that's K. And we want to solve for K. So what we're going to do is we're going to rearrange the rate equation so that we can solve for K. And you can see here we have the base equation of rate being equal to K times the concentration of nitrogen monoxide squared times the concentration of oxygen. We're going to rearrange this so that we isolate K. K will be equal to the rate divided by the concentration of nitrogen monoxide squared times the oxygen. So again, the rate divided by the product of the nitrogen monoxide squared and the concentration of the oxygen. We can now plug our numbers into our working equation. So K is going to be equal to the rate, which we just picked one of the experiments, and I think I picked experiment 1 here just to use the data from a consistent experimental set. We have the rate at 0.50 moles per liter times seconds. We're going to divide that by the concentration of the nitrogen monoxide, the square of that concentration, which is 0.10 moles per liter squared, and then also the product of the oxygen, 0.10 moles per liter. When we do this, we get a quantity of 500, and our units are liters squared on top over moles squared times a second. Now this K is true for any set of concentrations at this temperature. The only thing that will change K is the temperature itself. Also, just a caveat regarding the value of K. Units are very important, and it's very important that you keep track of your units here. And you can see this reaction rate constant, K, has some very strange units. But these units have to be there, because when you use K in a calculation to find concentration, for instance, it's the only way to ensure that you've set your equation up right, is if the units will multiply and divide in such a way as to give you what the final units that you're desiring to see, what you're looking for there. So be very careful that you cancel units properly and that you carry through what cannot be canceled. Let's see why K is so important. We're going to do some rate calculations using K. So we're going to determine the rate at which the reaction will proceed under the following conditions. Now we're going to assume the same temperature so that the value of K will be consistent. Our nitrogen monoxide initial concentration will be 2 moles per liter. Our oxygen concentration will be 1.5 moles per liter. So we're going to find the rate using our value for K times the concentration of the nitrogen monoxide squared and times the concentration of the oxygen. So here we have our numbers lined up in our equation. The rate is going to be equal to K, our 500 liters squared per mole squared times a second, times 2 moles per liter squared for the concentration of the nitrogen monoxide, times 1.5 moles per liter for the concentration of the oxygen. When we are done with this, we have our rate, which is 3,000 moles per liter times a second. So notice again how we make sure to be able to cancel our units and end up with a unit that is consistent with the rate of a reaction, which is in moles per liter times seconds. We are at the end of the Part 2 video podcast series on kinetics. I want to leave with a quote from Martin Luther King Jr. "A nation or civilization that continues to produce soft-minded men purchases its own spiritual death on the installment plan." Stay tuned for Part 3.